Okay, Green's theorem. Green's theorem. One moment, please. Green's theorem says that if R, well, let me just write this down first. Then I'll tell the conditions where these are equal. This is equal to the double integral over the region of dn dx minus partial m with respect to y times the area, times dA. These two are equal if R is a simply connected region and m, n, partial n, partial x, partial m with respect to y are all continuous in an open region containing R. And that's equal. Okay, so I'm going to verify the Green theorem by evaluating both intervals, the one on the left and the one on the right. And the path that we're going to have for the first one is a square. We start at the origin, we go 4 to the right, we go up 4, we go 4 to the left, and then we go down 4. Well, that means that R of t, now we did a problem just like that, so I'll be a little bit quick. It's ti as I goes from 0 to 4, of course, and then x is always 4, so it's 4i plus t minus 4j as t goes between 4 and 8, and then along here we have y is 4, so I guess we have 12 minus t in the I direction plus 4j, and now t goes between 8 and 12, and okay, I'll put it in the bottom. And then we go down, and that's where x is always 0, so we have 0i plus 16 minus t in the j direction. And t goes from 12 to 16. Okay. Well, let's do it the simple way first. What is, now remember, okay, so what we're giving is, y squared dx plus x squared dy. This here is m, this here is n. So the double integral, the partial of this with respect to x is 2x minus, let's say minus, partial m with respect to y is 2y. And our dA is just dx dy. And x goes from 0 to 4, and so does y. And if we integrate with respect to x first, we did x squared minus 2xy from 0 to 4, the integral of that dx. You plug in 4 for x, you get 16 minus 8y. Integrate that, with respect to y, dy. And you will get 16y minus 4y squared. And y goes between 0 and 4. You plug in 4, you get 64 minus 64, which is 0. Okay, now this made sense that the integral would be 0. It's conservative. Is it conservative? Actually, it was not. Well, let's see if it's conservative. The partial of n with respect to y. Since these two are not equal, it weren't conservative. Remember, if it's conservative and it's a closed path, it must be 0. And that's why this theorem said it had to be a closed path, a simply connected region. Because if these two are equal, of course when you subtract you're going to get 0. So the double integral of any region of 0 dA will always be 0. That wasn't the case in our problem, but nonetheless it happened to turn out to be 0 anyways. Okay, that's using Green's theorem. Now if we don't use Green's theorem, it's going to be a nightmare. Me personally, I'm not looking forward to working this out, but I will. Okay, so now along path 1, we'll call this path 1 and path 2, etc. Along path 1, we have x is t and y is 0. But if y is a constant, that means dy is 0. Okay. So, let's just do it here. Y is 0. 0 dx is 0. Plus x squared, or t squared, times 0. dy is 0. The first piece is going to be 0. Plus, what happens along the second path? You have that x is 4. X is 4. Y is t minus 4. So if x is a constant, that means dx is 0. So this first piece will be 0, because dx is 0. So then we get x squared, which is 4 squared, which is 16 dy. But y is t minus 4. So if y is t minus 4, then dy is dt. dt. And t goes from 4 to 8. T goes from 4 to 8. Okay. Let me erase this so I can have some more room. Now, for the third piece, x is 12 minus t, and y is 4. Well, if y is 4, that means y is always constant. That means dy equals 0. And if x is 12 minus t, that means dx is negative dt. Okay, so we have y squared. For y is always 4, so it's 4 squared, or 16 dx. The dx is negative dt. Plus x squared times dy. But dy is 0, so that kind of cancels out. And t goes between 8 and 12. Okay, that's the third portion. Now, let us look at the last piece, the left-hand side. X is 0. So therefore, since it's constant, not so much 0, but constant, that means dx is 0. And y is 16 minus t, So dy is negative dt. Okay? So dx is 0. That means this first integral is 0 plus the second half, x squared. Well, x is 0 times negative t. It's 0. It's just 0. Okay, let me erase the whole bottom, and we have two integrals to do. Because 2 of the 4 that are on this last line are 0. 0 and 0. Okay, the integral of 16 dt is 16t from 4 to 8 minus, I can factor this out as minus 16t from 8 to 12. I will factor out the 16 from everything. It's t from 4 to 8 minus t from 8 to 12. 16 times that. Well, this is just 8 minus 4, which is 4. Minus, this is 12 minus 8, which is 4. Well, 16 times 0 happens to be 0. So we got 0 in both methods. This last one, a little bit harder. That is why some great mathematician, possibly by the name of Green, I'm not sure, came up with Green's theorem. Hey, it took a while, but that's the first problem we've done. How about we want to integrate y minus x dx plus 2x minus y dy. And C is the region in between y equal x and y equal x squared minus x. It's the region bounded by that. So let's graph this. Can factor out an x here. So now I know the zeros. It's a 0 at 0 and at 1. And it's a positive x squared, which means it goes this way. And y equal x, of course, goes this way. And they intersect at 0, 0, and wherever else the two y values are equal. Bring this to the left side. We're actually bringing it to the right side. X squared is 2x. Well, 0 squared is 0 times 0, is 2 times 0. And think of x squared as x times x. So you have x times x equals 2 times x. I'm multiplying this by x, I'm multiplying this by x, and I'm getting equality. That means x is 2. 2, remember x equals y. 2, 2. So that's the region we are integrating. Actually, let me be clearer than that. Is this right here. The area inside that ring. Okay. Now, I would call this M. I would call that N. And then I would invoke Green's theorem. I know that this is equal to dn dx minus dm dy dA. But what is the partial of this, including the plus sign, with respect to x? Answer is 2. With respect to y, the answer is 1 dA. Well, the integrand is just 1. It's 1 dA. Well, this is an integral of dA is dy dx. Well, what does y go from? it goes from here to here. Well, down here, y is x squared minus x. And up here, y is x. So it goes from x squared minus x to x. That's why I put dy first. I don't want to do dx first because, for example, above the x-axis, it's that minus that. And I know that x. Right there, x is y. Now, if y is equal to x squared minus x, it's hard for me to say what x equals. And then, below this line, I have different x's. Maybe this x is the same as that one, whatever that is. But I don't know what this x is. So definitely want to do dy first. And then x goes from, the smallest x can be is right there, which is 0. And right there, x is 2. The smallest x can be is 0. The largest it can be is 2. And that's a straightforward double integral. I'm going to leave it like that. And it's a lot easier than going along the path. We just converted it to a standard double integral. It's independent of the path. Now we have this one. The integral of 2xy dx plus x plus y dy. And c is between y equals 0 and y equals 4 minus x squared. Well, minus x squared is an upside down u centered at the origin, but we're adding 4. It's that. And y equals 0 is this. So the region we're talking about is this region here. This region in here. Okay. So this is m, including the plus sign that's n. Now, dm dx, dy, is just 2x. And dn, dn dx is just 1. So, the double integral of 1 minus 2x. This minus that, dA. Real quickly, we convert it to a nice simple integral. And then we have to find dA. Either I'm going to say dx dy or dy dx. I know the y value down here, and I know the y value up here. So I'm going to draw my slices this way. I'm going to say dy dx, and dy goes from 0 to 4 minus x squared. And x goes between -2 and +2. Find their x-intercepts, plus or minus 2. And there it is, work that out. A Green theorem, powerful theorem. I wish all, quote, hard problems were easily converted to easier ones. Now, suppose you had the integral of x, y dx plus x plus y dy. It's between the area you want to integrate is integrate over, that is, it is between that circle and this circle. Circle of radius 1 and circle of radius 3. 1 and 3. I'm going to integrate in here. I'm going to integrate over that area. Okay. This is M, and this is N. M before N, if and only if X is before Y. Whatever is being multiplied by dx, that's M. Whatever being multiplied by dy, that's N. Okay, so now the partial of N with respect to X is 1, and the partial of M with respect to Y is X. So this becomes integral of 1 minus X. The double integral of 1 minus X dx. dA. Now, have to be a little bit careful here. What I'm going to do is, first I'm going to integrate that over the whole big circle, the whole thing. That is, this is the double integral of 1 minus X. Now you know what? I think it's better to just go polar. X is R cosine theta, and R dr d theta, and R goes from 0 to 3, and theta goes from 0 to 2 pi. But then we want to take away everything inside this circle. And that gives the area we want. 1 minus X dx dy becomes R dr d theta. The R goes from 0 to 1. That's the radius. It's 1. Originally it was 3. But now we're taking away from 0 to 1, and theta still goes between 0 and 2 pi. Integrate that, get your answer. That was a bit tricky in my opinion. But that's why I chose to do it. Okay. Now, we have this theorem. Goes on to say that if R is a plane region bounded by a piecewise, smooth, simple, you need to know what all of these words mean. Closed curve C. Then the area of R is 1/2 the integral of x dy minus y dx over that closed curve. Now, in our problem, you are told that R is the region in between y equals 2x plus 1 and y equals 4 minus x squared. Well, 4 minus x squared, it looks like this, and y equals 2x plus 1 looks like that. And if you set the y's equal to one another, you'd find out that x was 1 here, so y is 3, and down here x is negative 3, so y is negative 5. You would find that. So along, say, the top curve, you know that y is 2x plus 1. So that would imply that dy is 2 dx. And along the second piece of curve, we know that y is equal to 4 minus x squared. So dy will be negative 2x dx. So what we get is the area equals 1/2 x dy. Now, along curve 1, so it's the upper curve minus the lower curve. It's the upper minus the lower. The upper is what I'm calling C2. So it's 1/2 x dy, but dy is 2x, excuse me. We're going along path 1. We're actually going this way, okay? So it's x times dy, but dy is 2 dx, minus y, which is 2x plus 1, excuse me, times dx. So it's that integral minus, now we go over the other curve, C2. Excuse me. X times dy. X, just reading here, x times dy. dy is negative 2x dx minus y, which is 4 minus x squared, 4 minus x squared times dx, which is negative times dx, excuse me. And this integral goes from negative 3 to 1. Goes from negative 3 to 1. Now, look, so let me get rid of this, please. Let's clean up this integral a little bit. It looks like a mess. So, it's 1/2 the integral from negative 3 to 1. X times, so everything is times dx. I can factor it out. X times 2 is 2x minus 2x minus 1. This is minus 2x, but I take it away, minus 1. So I take away minus 2x, that's plus 2x. This is minus 4, but I'm taking it away, so it becomes plus 4. I'm adding x squared inside there, but I have to take it away. So I take away x squared. And this is all times dx. Well, that of course cancels out. And you get negative 1 plus 4 is 3, plus 2x minus x squared dx. And that's exactly what you want to integrate. actually, that's negative 2x squared. And then you take it away, so it becomes plus 2x squared. So the 2x's cancel, and you have 2x plus minus x squared is x squared. So this silliness there, the errors, it's the concept that matters, x squared. And then you have plus 4 minus 1 is plus 3. So you integrate that, which is very straightforward. It's x cubed over 3 plus 3x, evaluated from negative 3 to 1. And I'll leave you with that to do. Plug 1 in, plug negative 3 in, then multiply that answer, subtract, and multiply that answer by the half, which is in front. You definitely should use this theorem. It makes life a little bit easier. It tells you the integral. And the next one I'll do, next and last one, is I want to prove a silly theorem. It's very, very simple. Suppose you're given an integral of a function of x times dx plus a function of y dy. Now you want to show that this is always equal to 0. And of course it is, because this is m and this is n, and dn dx. The partial of this with respect to x is 0. It's just a function of y. Maybe it's y cubed plus 2y plus log of y all over the fifth root of y cubed plus 1. With the partial of this with respect to x is 0. You know what? The partial of m being just a pure function of x, the partial of n with respect to y is 0. So by Green's theorem, we get the partial dn dx minus partial m dy times dA. But 0 take away 0 is 0. The integral of 0, the double integral of 0 over any area is 0. I mean, you can work this out as the double integral of 0 dx dy. X goes from one function of x to another function of x. Y goes from a to b. The integral of 0 dx is 0 from f1 to f2. It's 0 minus 0, which is 0. From this is 0. 0 dy, the integral of that is 0. From a to b is 0 minus 0, or 0. From right here, you should say, oh, I'm integrating over 0. The answer is 0. Okay, so that completes that section. Section on Green's theorem.